To fulfill the design requirements and to measure the success of the objectives, I started my design process doing some general research of the aerodynamic concepts. Using online resources, I needed to make a determination about the 3 key design aspects I would focus on: wing placement, wing shape, and dihedral angles. I discovered that the center of gravity should be about 25% of the wing's chord length back from the leading edge. I also found out that the horizontal stabilizer should be around 20 to 25% of the wing area, while the vertical stabilizer should be around 40 to 50% of the horizontal stabilizer area. I also researched the trade-offs between high and low wing configurations. Low wings are less susceptible to drag, but high wings are more stable because the CG is located under the wing. For the wing shape, I learned about the trade-offs between drag stability and maneuverability between longer wings and shorter wings, and ultimately discovered my aspect ratio should be around 4.7, while the approximate angle of attack I should have on my wing was 3 degrees. I also found out about the dihedral effect and how it can make an aircraft more laterally stable, as well as how tapering a wing can reduce induced drag. By incorporating all the research I gained, I created my first model proposal using Google SketchUp. To make sure the glider kept intact as per the requirements, I chose to base every design choice off of improving stability. For example, the wings would have a dihedral angle of 3 degrees to improve lateral stability, while being slightly tapered to reduce drag. The wings had an aspect ratio of 4.7, which was optimal according to the research. The design also had a slight 3 to 4 degree angle of attack to improve lift, and ideally would have been cambered using lightweight paper to improve lift. Also, it would use high wing configurations because of its stability benefits. As previously stated, my 3 alternatives were wing placement, wing shape, and dihedral. Through testing, I was able to weigh the pros and cons for each to get my official final design. I created a balsa cardboard prototype out of scrap pieces that was a scaled down version of the final design. In this prototype, I would have basic square horizontal and vertical stabilizers made out of cardboard and test out slightly tapered wings with a paper airfoil. The wing would be mounted at a 2 to 3 degree angle of attack. First, I tested the CG placement using a glue stick to try to balance the plane over 1/4 the wing chord. What I immediately realized is that the wing shouldn't be close to the nose. Also, what affected the CG the most was adding mass using Play-Doh rather than moving the wing. So in the end, I decided to place the wing near the middle of the fuselage and add mass to the nose to compensate for any imbalances. Now it was time for the test flights. Through a series of over 10 test flights, I discovered that the glider didn't generate enough lift for the 20-foot minimum target. Now it was time to investigate alternative wing shapes. So to improve the lift capabilities while keeping the 16-inch dimension limitation in mind, I added some more wing area behind the initial wing. After doing some more testing, I was satisfied with the amount of lift being generated, but the extra lift amplified a problem that I had not initially seen. Unfortunately, the glider was veering to the right. I attributed this to the manufacturing issues, and after some light investigation, I realized the dihedral angle was not the same on both sides of the wing. So I tested the glider again after taking out the dihedral angle, and the plane flew with far better stability. Ultimately, I decided not to have a dihedral on the final design. After this test, I decided to round out the wingtips to reduce induced drag, and at this point, I was happy with the design modifications. I created the final design, which I named Elevate, with a wingspan of 40 centimeters to maximize the wing area without breaching the 16-inch limitation. It also had a total wing area of 396 square centimeters. I made the wings using 2 different balsa pieces, so I decided to angle the back piece of the wing like flaps, rather than setting the whole wing at an angle of attack. I created the airfoil by cutting out balsa ribs and covered them with paper. For the horizontal and vertical stabilizers, I connected them in a lap joint style. I also slightly tapered the front edge of the stabilizers for a more streamlined look. Finally, I glued on the wings and stabilizers using C8 adhesive. I did a few tests of the final design and realized the wing was not put on completely horizontally, but thankfully I was able to compensate for this imbalance by changing the angles of the flaps until it flew straight. All my design tests and iterations culminated in one final successful test flight in which Elevate flew over 40 feet. After a few more aesthetic enhancements, I knew Elevate was ready for flight day. In round 1 of flight day, Elevate was able to make 43 feet, and though it was eliminated in round 2, it managed to fly even further to 52 feet. Overall, I was satisfied with my glider's performance given the windy conditions on the day. Using the flight test footage, I reported an angle of attack of 8.5 degrees and used the thin airfoil theory to get my coefficient of lift, and then calculated the coefficient of induced drag to find my coefficient of drag. Finally, for my center of gravity, with the amount of Play-Doh I added onto the nose on the test day, the CG location was about 1.5 centimeters back from the leading edge. Overall, I'm proud of my design and especially the utilization of an airfoil to improve the lift capabilities. If I had more time to improve the design, I would make sure that the wing was attached completely horizontally and ensure it was balanced properly on both sides, using the laser cutter for better precision in manufacturing.